Hey everyone, so we are into chapter 16, which is electrochemistry. So it's kind of where chemistry and electricity converge, as you could guess from the title. Today what we're going to be talking about are voltaic, or also known as galvanic cells. Okay, and pretty much what they do is they turn chemical energy into electrical energy. So what I'm going to be doing is I'm going to show you a galvanic cell, I'm going to show you how it works, and then later on we're going to be able to do some calculations where we're actually able to calculate how much electricity this cell will produce based on its anode and cathode, which we will talk about later. So let's go ahead, let's draw one of these cells and let me show you how these things actually work. Alright everybody, so this is our galvanic cell, or our voltaic cell. And what it is it's two beakers with solution in them. This one happens to be zinc nitrate, 0.1 molar zinc nitrate in this beaker, and the only thing that we really care about is the zinc 2 plus. So when the zinc nitrate goes in this beaker, it dissociates into nitrate and zinc 2 plus, but we only care about the zinc 2 plus. And inside of it is a zinc anode. Okay, so this is just a piece of zinc metal that's sitting in there, and it's connected to a wire over to another beaker. But in this other beaker there is a strip of copper, and it is in copper nitrate solution. So again, we just care about that Cu2 plus charge that's sitting there. We got this meter here that's measuring the electricity. As you can see, I have the electrons flowing from zinc to copper. And then connecting these two beakers also is a salt bridge, which we will talk about later. So what is causing this flow of electrons? Okay, so the electrons from this zinc metal are going to this copper metal, and that's just due to a difference in voltages or standard reduction potentials. So what you'll do is you'll look at the standard reduction potential worksheet that I attached below this video. And as you can see, there's a list of all sorts of elements going through a reduction phase. There's some fluorine, there's hydrogen in the middle at 0, and there's all these bunches of metals. Well, the higher up you are on that list, the more likely you are to attract electrons or get electrons or be reduced. So what's happening is, if you look at that list, you'll see that copper is much higher on the standard reduction list than zinc. So if we put those two metals together in a galvanic cell, zinc will transfer its electrons over to copper because copper wants them more. You might also see on there that there is a fluorine at the very top that has a really high positive standard reduction potential. If this were a galvanic cell, and instead of having zinc over here, I had fluorine over here, that has the more positive standard reduction potential, so those electrons would flow to the fluorine instead. But we're not dealing with that. We're dealing with zinc and copper. So let's go ahead and let's see what's happening at a microscopic scale. So because of those standard reduction potentials, copper attracts those electrons a lot more than zinc. So what's happening is zinc is giving up those electrons. So let's zoom in on that piece of metal right here. We have a bunch of zinc atoms chilling in this piece of metal. Obviously I'm making them bigger so you can see what's going on, and that wire comes out, and remember, it's in that beaker that is full of 2 plus. Well, what that zinc does is that zinc goes ahead and it gives up 2 of its electrons. Well, when zinc gives up 2 of its electrons to go over to copper, guess what that zinc turns into? It turns into zinc 2 plus. Okay? So what that zinc is doing, that solid zinc, is essentially it's giving up its 2 electrons, and that's turning into aqueous zinc. It's turning into this zinc nitrate solution. So this zinc will keep doing this, and eventually all of this solid zinc is going to turn into aqueous zinc. So that zinc piece of metal is going to get smaller and smaller. Let's go ahead and let's look at the other side. If we're looking at the other side, right, we got some copper floating around here. We got that copper metal, right? And we got some copper 2 plus. floating around here? Well, remember, now the electrons are coming in to the copper side of this galvanic cell. So what's happening is that these electrons are going to this copper, and these liquid Cu2+, these aqueous Cu2+, are taking those electrons, and they are going from aqueous to a solid copper. So what we're seeing is that zinc is losing electrons, and the solid zinc is becoming aqueous zinc, while on the other side, the copper is accepting electrons, and the aqueous zinc is becoming, or the aqueous copper, sorry, is becoming solid copper. So we're essentially losing zinc metal, turning it into aqueous, and taking copper aqueous solution and turning it into more copper. So what you will see when this happens is you'll see the zinc deteriorate eventually, and the copper become larger and larger. So this is what is going on in this galvanic cell. It's transferring electrons, that copper is becoming solid, that zinc is becoming aqueous. And what's happening to each of these? What's the chemical reaction that is happening in each of these? Well, zinc is going from zinc solid, and it is becoming zinc aqueous and is losing 2 electrons. Okay? So zinc is losing 2 electrons. So remember, when it loses electrons, it is being oxidized. Okay? So since zinc is losing electrons, it's becoming oxidized. Well, on this side, it's copper 2+ aqueous. It is receiving those 2 electrons and becoming copper solid. So here, copper is gaining electrons. Remember, gaining electrons is reduced. So what we have here is we have an oxidation-reduction reaction where zinc is being oxidized and copper is being reduced. Okay? And usually whatever is getting oxidized, that side is known as the anode. Okay? The oxidized side is the anode. So this zinc is known as our anode. Whereas the reduced side is known as the cathode. Now remember, we have our saying for knowing if something is losing electrons or gaining electrons. It's Leo says Gur, right? Losing electrons, like zinc did, it got oxidized. Leo. Losing electrons, oxidized. Gaining electrons is reduced. Gur. Well, we have another one for remembering that the oxidized side is an anode. We have the saying anox, right? Anox. Oxidation happens at the anode. For this one, reduced cathode, we just say red cat. Reduction happens at the cathode. So when you're looking at these galvanic cells, you might have to identify which is the anode and which is the cathode. In this case, whichever one is gaining electrons, which one is higher up on that standard reduction potentials list that is posted below this video, is the reduced one. It's the cathode. So in this case, it was copper. The oxidized one is the one with the lower standard reduction potential, like zinc. It loses electrons, it is oxidized. It is the anode. So that is some of our identification that we're going to have to do. We're going to have to show the flow of electrons. It's going to go to the higher up standard reduction potential. We're going to have to be able to understand what is happening in these galvanic cells, which causes these electrons to transfer. And we're going to have to identify anode and cathode. Another thing we're going to do next is we're going to have to be able to calculate the voltage that is transferred from these two, and we got to be able to understand this salt bridge. So let's go ahead and let's talk about the salt bridge next. So here is looking at our galvanic cell, again at kind of like a zoomed in molecular level. They're still connected by that piece of wire, and now in the salt bridge, I have identified the ions that are in the salt bridge. It's salt, okay? I got NaCl in here. It could be maybe like potassium and chlorine, or it could be, I don't know, let's go with a nitrate and maybe calcium, something that is easily dissociated that will help with this galvanic cell. So what does that salt bridge do? Well, as you can see, this reaction has been going for a while, and our zinc is getting pretty small. It's getting a lot skinnier here. Our anode is almost gone, and our cathode is getting very large on the right side. A lot of that aqueous copper has turned into solid copper. Well, after that happens, remember this zinc is getting put into zinc 2+. So I'm getting a lot of buildup of zinc 2+ over here. And remember on this side, that aqueous copper, that Cu2+, is getting turned into neutral copper. So really all I'm getting left with is that spectator ion of NO3-. So what we're seeing is we're seeing a bunch of positive charges in this beaker and a bunch of negative charges in the other beaker. Well, when that happens, the flow of electrons will stop. Electrons will flow when there is a cell potential difference. There's a difference in charges. Well, if you get too much positive and too much negative, those electrons aren't going to flow anymore because they're going to say, it's too negative over here. I don't want to go by a bunch of other electrons. So this is where the salt bridge comes into play. The salt bridge will help neutralize those beakers. So we have too much 2+ over here. Well, Cl- is going to come in here, and it is going to keep everything under control. So some of that Cl- salt is going to come in there and neutralize that positive charge. Here we got that negative nitrate because we're eating up all our Cu2+. Well, the Na is going to come in here and neutralize this party. So now electrons could keep on flowing. We could keep taking electrons from the zinc and bringing it over to this copper. So that's what the salt bridge does. It just makes sure that one side is not too positive and not too negative. So this thing can keep going for a little bit longer. It also helps connect the circuit in a way, right? So that is what the salt bridge does. Okay, we get too much of a buildup on both sides. That salt comes in and helps neutralize things up. So now let's go ahead and let's talk about how we are going to calculate this cell potential or this voltage from these galvanic cells. So now we are going to talk about which way those electrons flow and how we calculate the voltage of those electrons. So if you look at that standard reduction potential paper that is underneath this video, you will see a whole list of standard reduction potentials that tells you the voltage or the electricity that these elements like to give off. And remember, the higher up you are on the standard reduction potential sheet, the more likely it is going to attract electrons. And as you can see, it gets more positive as we go up. And what does a positive cell potential mean? So if we have a positive cell potential, or E naught, that means that it is thermodynamically favored. Okay, thermodynamically favored, which also means spontaneous. Okay, if E naught is positive, that means that the reaction happens on its own. It is thermodynamically favored. Spontaneous is a good way to understand what thermodynamically favored means, but the AP exam prefers you say thermodynamically favored. So that just means that the reaction will happen on its own. Okay, if the cell potential is negative, that means it is not thermodynamically favored. Or it is not spontaneous. So in some reactions, the electrons will just flow on their own, and that is when the E naught or the cell potential is positive. When they are negative, that means it's not thermodynamically favored. It means it's not spontaneous. That means you have to use something like a battery to make the charge happen, right? Sometimes we don't want electrons to flow automatically. Sometimes we want to have control, and that's where a battery comes into play. Okay, so when we're looking at the standard cell potentials, you know that the more positive it is, the more likely it is it's going to attract those electrons. So when we go to our list, we find copper and we find zinc, and we look at those two, and we realize that copper is more positive, so it is going to stay reduced. All of those reactions in that list are reduced, and copper is the highest one, so it's going to stay as Cu2 plus 2 electrons and Cus with a cell potential of 0.34. Okay? Well, whatever your other reaction is, it's no longer going to be reduced. It's going to be oxidized, right? The one that's higher up is the one that's going to gain the electrons, so that's our copper. Well, the other one's not going to be reduced anymore. It's going to be oxidized. So we're going to flip this reaction, okay? Since it was more negative, it's not going to be reduced, okay? We're going to flip it. So it's zinc solid. And it's going to make zinc 2 plus and 2 electrons. And now since we flipped it, we also are going to flip the sign of the cell potential and make it positive 0.76. Alright, so again, I give you two metals, an anode and a cathode. You look at them on the list. You keep the more positive one the same. Since copper was more positive, we kept it the same. The other one is what's going to be oxidized, so we flip it like I did down here. And when you flip it, you got to flip the sign. So then what we do if we want to figure out the cell potential, we just add these two voltages or cell potentials together, and we will get a total of 1.10 volts created from this reaction. And the reason why we're just able to do that is because they each have 2 electrons and they cancel out. Okay, so the whole reaction for this thing is going to be zinc solid plus Cu2 plus is going to make copper solid and zinc 2 plus. Okay, so this is another thing that they're going to want you to do. They're going to want you to figure out the cell potential, and that just comes from looking at what's in your galvanic cell, looking at the cell potentials here. The more positive one stays the same. The smaller one, or the more negative one, is going to be flipped. Okay, let's talk about some cell notation, and then we'll tie all this together. All right, so the next thing we're going to talk about is cell notation. And this is just a way to define a galvanic cell. Sometimes it's just not really fun to draw that galvanic cell a bunch of times, right? It takes a lot. It's a beaker, it's a salt bridge, it's a voltage meter, okay? So what you can do is instead is you could write this thing called cell notation. And for that galvanic cell that we drew, the first part is that we'll have zinc solid, which was our anode, divided by a line. And remember that the electrons left it and it became zinc 2 positive aqueous. Okay, so that's the left part of our cell notation. And then you'll have 2 lines that show that we are going to a whole another beaker. This new beaker being CuAq 2 plus, remember that copper aqueous is now becoming copper solid. So this is cell notation. So this tells me what's going on in a galvanic cell without me drawing all that stuff. It's zinc solid becoming zinc 2 plus aqueous, so it is being oxidized, it's losing electrons, and then it's Cu2 plus becoming Cu solid in the other beaker. It is being reduced. Okay, so that is cell notation. Now let's do an example involving this galvanic cells. So the first question or example I'm giving you is I want you to draw a galvanic cell between lead and iron. So you'll have a galvanic cell, you'll have a salt bridge, you'll have an anode and a cathode, and you'll have the electrons flowing from one to the other. So let's go ahead and let's show a galvanic cell. So we'll have a galvanic cell happening here, right? We know we'll have some sort of solution. We know we'll have a metal over here and a metal over here. We'll know they'll be connected by a wire and some voltage meter. And we know there will be a salt bridge. Okay, and we know we're dealing with lead and iron, so let's just put lead as one of these and iron as the other. It doesn't really matter. Let's just put lead over here and iron over here. Okay? And now what I'm going to ask you to do is I'm going to ask you to show me which way the electrons go in this. Are they going to go from lead to iron or iron to lead? What's the cell potential? And what's the overall reaction for this? And maybe some cell notation too. So the first thing I want to do is I want to go to my standard reduction potentials worksheet and I want to figure out the reduction reactions for both of these. So I'm going to go to that standard reduction potentials sheet and I'm going to look up lead and I'm going to look up iron. And if I look up lead, its reduction reaction is Pb2 plus Aq plus 2 electrons will make Pb solid, okay, and its electron reduction potential is negative 0.13. So its E naught is negative 0.13. So I know that the other lead ion in here is going to be lead 2 plus. Okay, sometimes they don't lose 2 electrons at a time. Sometimes they only lose 1 electron at a time. Copper could lose 1 electron at a time. But since we know this is losing 2 at a time, it's Pb2 plus. Let's go ahead and let's look at iron. Iron's is Fe2 plus Aq, 2 electrons, and it makes Fe solid. And its E naught is negative 0.44. So once again, we know this is losing 2 electrons at a time, so I could just put Fe2 plus. So now I'm looking at this, and I might ask you, which way do the electrons flow? Which way do the electrons flow? Well, remember, they will go from the most positive E naught. Okay, so which one has the more positive or the larger E naught? Which one's going to attract electrons more? Lead. It is the greater number. It's not positive, but it's a lot less negative than 0.44. So that means that those lead anode or cathode, we're not sure yet, that lead piece of metal is going to attract electrons. So the electrons are going to flow from the iron to the lead, and that's just because its E naught is more positive, right? So now I might say label anode and cathode. Well, remember, oxidation happens at the anode. Okay, oxidation happens at the anode. And if we know about Leo says Ger, losing electrons means oxidized. Losing electrons is oxidized. Well, iron is losing the electrons, right? The electrons are going to lead. So iron is losing electrons, so it is oxidized. And remember our other saying, anox, so oxidation happens at the anode. This is our anode. So that means that this is our cathode, right? Red cat, reduction at the cathode. Ger, gaining electrons is reduced. This guy's gaining electrons, so this is our cathode. Cool. C, I might say, calculates cell potential or E naught. Okay, that's just the electricity. Remember that the one that's being reduced will stay the same. So lead is reduced, so it is staying as is. But remember, iron is being no longer reduced. It is losing electrons. It is oxidized. So remember, we got to flip this guy. So we'll have Pb2 plus 2 electron negative is Pb solid, and it is still negative 0.13 because it's reduced. But iron now, which is oxidized, we have to flip it, and it is going to become Fe2 plus Aq. These are both Aq, by the way. And 2 electrons. And now since I flipped it, it's no longer negative 0.44. It is positive 0.44. So we add those together, and we'll get a 0.31 volts as my C. And I might ask you, is this spontaneous or is this thermodynamically favored? It is. If it's positive, it's thermodynamically favored, or it's spontaneous. This will happen on its own. I don't need a battery, okay? If it was negative, it'd be not thermodynamically favored or non-spontaneous. And now I might ask for the cell notation for my last one. So cell notation. Okay, let's go ahead and let's do this. Let's go ahead and do the left side, right? So let's see, lead is gaining electrons, so it's going to become Pb2 plus and become Pb, right? If it's gaining electrons, let's do that over here. It's going to go from Pb2 plus Aq to Pb solid, right? If it's being reduced, it'll go from Pb2 plus, it's gaining electrons, it's going to become Pb solid. While the other side is going to go from iron solid to iron 2 plus aqueous. So that is our cell notation. Left side, Pb2 plus is becoming Pb solid because it's gaining electrons. The right side, Pb or Fe solid is becoming Fe2 minus because it is losing electrons. And the last thing I might do is just show me the chemical equation for this whole thing. And all we're doing is we're just combining our two half reactions, our two standard reduction potentials, which is going to be Pb2 plus Aq plus Fe solid, and it's going to become Pb solid and Fe2 plus Aq. So there's a lot of questions that come with these types of problems. A lot of things I'll want you to identify. So let's go ahead and let's do one more example. So last example, it says, write the equation for the reaction that occurs when an Ag half cell reacts with a Cu half cell and calculate the cell potential. So here, it's wanting us to figure out a whole reaction for a half cell, that's galvanic cells. And the best way to do that is look at our standard cell reduction potentials and look at these reduction half reactions for both of these guys. So if I were to look at Ag's half cell reaction from the standard reduction potential worksheet is as such. Ag plus aqueous plus another electron becomes Ag solid, and it's got a cell potential of positive 0.80. Okay? And the next one is Cu2 plus Aq. It's going to gain 2 electrons. We've dealt with this before. And it's Cu solid, and its cell potential is positive 0.34. So we have our half cell reactions, and the best way to figure, or the first thing that we got to figure out is which one is going to be reduced and which one is going to be oxidized. Well, remember the more positive one is the reduced one. Well, in this case, the more positive one is Ag. Okay, so we're going to flip this one, and it's going to become oxidized. So let's go ahead and let's flip this guy into Cu solid to Cu2 plus 2 electrons. And now it's not positive 0.34, it's negative 0.34. Okay? All right, so then if you want to find cell potential, that's pretty easy. We just add these together, and you'll get positive 0.46 volts. Okay, so that's an easy way to calculate cell potential. But now, what we've got to do is we got to combine these guys. Well, in order to combine these guys, the electrons have to match up. Here, the electrons don't match up. We got 2 electrons in our copper and 1 electron in our silver. Well, what we do there is we just multiply everything by 2 in our silver reaction. So that's going to be 2, that's going to be 2, and that's going to be 2. Important thing to note here. This does not change, okay? Even though I multiplied all this by 2, do not multiply this by 2. These cell potentials will never change. That is a common mistake with these types of problems, is that people are like, oh, times 2, 2, 2, 2, I'm going to multiply the cell reduction by 2. Don't, okay? We don't care about that, all right? It stays the same. We already calculated cell potential. Sometimes that's why it's good just to calculate cell potential first if possible, okay? So again, never touch this, but it's all right to multiply all these. Well, now when we combine them, the 2 electrons will cancel out, and we'll be left with the equation 2Ag aqueous plus Cu solid will make Cu2 plus aqueous and 2Ag solid. That way we have a balanced equation. The silvers are balanced, the charges are balanced, and we have a nice little equation here. Okay, so that is galvanic cells and cell potential. Your best friend is that standard cell reduction sheet. We should be able to draw a galvanic cell. We should be able to understand what the salt bridge does. We should be able to calculate cell potential. We should be able to give a total reaction for this. And we should be able to use cell notation to help simplify a galvanic cell, as well as identify the anode and the cathode and which way the electrons will be flowing. So that is galvanic cells. There's some practice below for you to try so you could get the hang of this with some answers attached. Please give that a shot. Let me know if you have any questions. Have yourselves a great day.